Hey everyone, Paul Lake here with another physics problem solved. This is the channel where I solve the physics homework problems provided to me by my tutoring clients. Take a look at the video description below for a way to contact me if you need a private tutor. My rates are reasonable and I'm really good at this. And if you find this video helpful, please like it, share it, subscribe it with others, and let's get to today's problem. Now here's what you need to know. Here's what we got. We got a bead that's going to slide around this wire. You're going to need to know this concept, conservation of mechanical energy. Move this over. So you're going to need to know this. So this means you need to know what mechanical energy is, right? It's the sum of kinetic and potential energy. And we are going to be we're going to draw a free body diagram, I think for part B, right? So you need to know how to do that. And let's see, what else? Yeah, I think that's good. And oh, well, yeah, you're going to need to know how to handle centripetal. I knew there was centripetal force. You're going to need to know how to handle a situation with rotational motion and centripetal force. Okay. Now, let's read through the problem. We have a bead, and here's the bead. It's got a hole in it. It's going to slide around this wire. The wire is threaded through a hole in the bead, and the bead slides without friction around the loop. Okay. The bead is released from rest. Okay. Oh, that tells me, okay, V equals 0 right here. At a height of 3.8. So this is what's given. So I can say H is equal to 3.80 times the radius. And what is its speed at point A? And shoot, this should be G. Use the following: the acceleration due to gravity, G, and R. And how large is the normal force on the bead at point A? If its mass is 4.5 grams. Okay, so we have a mass of 4.50 grams. And we want the minimum height for part C. We want what is the minimum height from which the bead can be released if it is to make it all the way around the loop. And so, that one's pretty straightforward. So anyway, for part A, what are we trying to find? What is its speed at point A? So we want V at A. Okay. Now, one of the things you need to do is classify a problem. And thus far, you've dealt with kinematics, you've dealt with force, and in combination with kinematics. But you really don't want to approach it that way, because this thing is not like the force that's pulling this thing down is a force of gravity, right? But it's a component of the gravity, and that component changes. This is a curved shape. Like the kinematic equations won't work for this, right? Because they only work for situations where the acceleration is a constant. But here the acceleration of this bead is constantly varying. So, and if you have that kind of situation and they're asking for your final speed, quite often the best set of tools to use is energy. So this is an energy problem. So, so let's solve this using energy. Now, when you have a situation where the only force that's doing work is the force of gravity, or the force of springs, but springs really aren't part of this problem, you can say that mechanical energy is conserved, right? And that's the conservation of mechanical energy. Once I lift this up, this thing has gravitational potential energy. I release it. It slides down. So as it goes down, it loses gravitational potential energy, but it gains an equal amount of kinetic energy. And so the sum of those two energies, the potential plus the kinetic, that sum is going to stay constant throughout this whole problem. And so we're going to use that idea to help us. I'm going to call this the initial position. And so E is mechanical energy. The initial mechanical energy is going to equal our final mechanical energy. This is the situation. This is how you start a problem if the only force doing work is gravity. Okay, just do this. Now, now I want to expand this idea out. Mechanical energy is defined to be the kinetic energy plus the gravitational potential energy plus the elastic potential energy. And of course, this is in my initial state. So I'm going to put an initial right there. And this is going to be the final kinetic energy plus the final gravitational potential energy plus the final elastic potential energy. Okay, now a lot of this stuff we're going to get rid of now because this is kind of a general expression and this is it expanded out for all different kinds of situations, but we want to apply this to the situation we have. And notice that at the initial state it says the velocity is 0. Well, that means it's got no kinetic energy, right? Now it does have height. Okay, so we're going to include that, and then but springs are really not. There's no compressed or stretched springs in this problem, so there's really no elastic energy to speak of. Now at the end, it is going to be, this bead is going to be moving at part A, so it's going to have kinetic energy, and it has height, so it's going to have gravitational potential energy. So this is what I'm left with. So now I can say, well, this is gravitational potential energy is mgh, right? Because that's its initial. And then this is going to be kinetic energy at point A. Well, kinetic energy is 1/2 the mass times its velocity squared. Okay. And then at the end, it's going to have its final height, mgh final. Okay. And now, take a look at this expression, and there's stuff that goes away, right? We've got the mass cancels out because it's in every single term. And this is what I'm solving for, right? I know what g is. I have an expression for the initial height, and I'm going to substitute that in. I'm going to do the same here. So let's go ahead and solve. This is my unknown, right? This is what I'm solving for. So let's solve for it. So first thing I'm going to do is multiply everything by 2. And that's going to be VA squared plus 2GH final. Now I'm going to put this on the other side. So it's VA squared is going to be equal to 2GH minus H initial minus 2GH final. Right? We put that over there. And then, of course, to get rid of that square, we're going to take the square root of this. Now I want to simplify this expression. I'm going to pull the 2g out, and that's going to leave h initial minus h final. Now, now I know something about these heights. Okay, they gave us some information about that because we want to do this in terms of the height. So the velocity at A is equal to the square root of 2 times g. Now, my initial height is given to be 3.80 times the radius. And then my final height, well, what is my final height? You see that it's one radius plus another radius. They didn't give us that, but they didn't tell us directly, but you can figure it out. It's twice the radius. Okay, now I can pull out an r. So let's do that. This is going to be 2gr. And then what's left in here is 3.8 minus 2.0, which is 1.8. Okay. Now I can combine, what is 2 times 18, right? 36, so it's 3.6. So I'm going to say that the applied force, the velocity at point A is equal to the square root of 2 times 1.8 is 3.6 times G times R. And I believe that is our answer. Okay. So if you use conservation of energy, it's pretty straightforward how you get that. Now, let's do part B. So I need lots of room here, so I'm going to do B right here. What are we trying to find? How large is the normal force of the bead at point A? So we want the normal force, F sub n, at point A. Okay, that's what those subscripts are standing for. Okay, so let's solve it. Now I'm looking at point A right here, and so I'm going to draw a free body diagram of that bead. And so here's the bead at the very top. Now it's got a hole in it, right? Okay, that the wire is slid through. Now there's no friction. There's no friction in this problem, so the bead and the wire there's no interaction that's parallel to the motion. And that's why it doesn't do any work. The normal force isn't doing any work in this problem. But, depending on how fast or slow this is going, you could have well, let's draw the forces acting on the bead. Well, we've got gravity like this. And then we've got a choice. Like, is the normal force, is it pushing down on it or is it pushing up on it? And so what I'm going to do is I'm just going to guess. I'm going to have it go down. So I'm going to say right at this interaction, we've got a normal force that's pushing down on it like that. And now, if you take a look at these forces, both of these forces are pointing down towards the center of that circle that it's moving. And this only happens when it's either at the very top or the very bottom of that vertical circle. But it's at the very top of this vertical circle. And that's a nice place because both of these forces end up contributing to the centripetal force, the center-seeking force, right? So let's make this positive y. I'm going to go down, and now let's sum the forces in the y direction equals ma in the y direction. And so now in the positive y direction, I've got this normal force. That's what I'm trying to find. Plus mg equals ma. Okay. So now what I'm going to do is I'm going to solve, well, a couple things. Let's solve for the normal force. So the normal force is just equal to ma minus mg. So I can pull an m out, right? I can say this is m times a minus g. Now I know what m is, that's given. I know what g is. I know what planet I'm on, okay? But what about the acceleration? Well, the acceleration, this is a centripetal acceleration. So this acceleration, we know, is equal to the velocity, and this is the velocity to point A squared over r, over the radius of the circle. And the radius of the circle is just this r that they gave us, the radius is moving around that circle. So we have now we have an expression from part A of this problem for the velocity at A, which is 3.6 times the square root of gr. But it's squared, so this is going to be 3.6 times g times r over r. Okay. And now, see where I got that from? I just took this, the velocity at A, you square it, that just gets rid of the square root symbol, and then you have that. So VA squared is equal to 3.6 times g times r. Well, r cancels. And so this is equal to 3.6 times g. So let's solve for that normal force. It's equal to M times A, which is 3.6 times G minus G. And so this is going to be the mass, and then we're going to have G, we're going to pull out a G, and this is 3.6 minus 1, that's 2.6. All right. And now we can plug in values. The mass was given to be 4.5 grams, but I'm going to change that 0.00450 grams, right? 1, 2, 3, right? You move the decimal over 3 times. It's 4.5 grams is 1, 2, 3, 0.00450 grams, okay? And that's the mass. And then we know what G is. G is 9.8. Oh, I'm sorry. I left it in. I'm changing it to kilograms, so I really ought to put kilograms there. And then acceleration of gravity is 9.81 newtons per kilogram. And then we have this 2.6 left over here. And when you do all this arithmetic, you'll get a normal force of 0.115 newtons. And there's my answer. Right? Because a kilogram cancels kilograms, leaves newtons. And if you want to put meters per second squared right here, it still comes out to be newtons. That's fine. You can do that. All right. So we're done with B. Now let's do part C. I think I can fit it into this corner right here. So what they want is like what is the minimum height so that this thing will make it around the loop? So the way I interpreted this problem is that it's moving around this loop, and so just when it gets to the very top, it barely has enough velocity to keep going and make it around the loop. So I'm going to say that the velocity doesn't reach 0, but it approaches 0 at part A, right? Or I mean at point A. It's just so it has enough tiny little bit of momentum that it keeps going around. So what does that mean? Well, that means that, I'm just going to use this. The initial energy equals the final energy. And, let me do this properly. What do I want to find? I want to find H, kind of the minimum height that I need so that it makes it all around. Okay. Now let's solve. So I'm going to say that when it's up here, its velocity is going to be 0. So I'm going to say that its initial mechanical energy is equal to the final. And then this is going to have mgh minimum, right? That's what I'm trying to find. And again, it's not moving. It's released from rest. So it doesn't have any kinetic energy. There's no springs. So it's all gravitational potential. And this is going to be equal to, well, when you get up here, it's kind of the same situation, right? I'm going to say that that it has mg, and then its height is 2r. And I'm going to say that its kinetic energy is 0, 1/2 mva squared. But I'm going to say that this velocity is just barely greater than 0. So it approaches 0. And that you can just treat that term as 0. So a lot of stuff cancels out here now. If this is 0, just the minimum height is just going to be 2r. It's just going to be the same height, right? If you take this and start the bead right here, and there's no friction, right? So that the bead will come down and it'll have just enough energy to get back up to where it started, and then it will slide back down, okay? So that's how I interpreted what they asked for there. And so there you go. All right. So this was a conservation of mechanical energy problem. Very, very common kind of problem. Hey, if you found this helpful, please give it a thumbs up. And that's thanks enough. If you're a physics student, you should subscribe to my channel and maybe share it with your friends. And send me a problem in the comments. If you go to the comments, you send me a problem, I'll work it, make a video out of it. And again, contact me if you need a physics tutor. And I charge, well, yeah, there's information there that will tell you how much I charge and how it works. It's all done online. It's all over Zoom and it works great. Okay, well, until the next problem, may the net force be with you always. That is all.